How are we doing today? A little bit louder this time, I guess. Good, good, good. It is good. We'll start on time at 9:30, but figured to get the chatting. So how many people are seniors here? How many people are grad students? Okay. All right. Do you have any research for as a grad student yet?
No, I'm trying to graduate soon.
Got it. So you're taking grad credit, but you're going to be graduated soon.
Yes.
Got it. Cool. Cool.
I am a grad student. I did graduate already.
Congratulations.
Thank you.
That's great. Yeah. And for those who don't know, if you go to anyone interested in grad school at all? A couple. Oh, I see various reactions. It depends upon the type of grad program you go to, but a big part of what you do in grad school is research for a lot of people, and that's one of the things that we encourage people using things in this class for, in order to control their systems. I'm going to use a lot of robot examples, but I'll make it clear there are lots of examples other than robots. So, all right, I think we're about ready to get started in another minute. How are we looking?
Great.
Great.
I guess we'll just have to start recording.
Oh, let's start recording there. You hit the record button?
It looks like that's the view, so we don't want it to.
Yeah. All right. I think we're slowly getting this whole technical setup already. Okay. We're still getting a lot of the website stuff together. It should be together soon on the Canvas page and hopefully my own personal web page, so you have easy access to all the lectures. We'll have the lecture 0 from the initial lecture up probably today. We'll have that so you can review it. On Thursday, we will have our first virtual coding lecture. Okay, so we'll be doing the same thing, except we will be on Zoom. You can participate via Zoom. You can talk to me via Zoom. You can ask me questions via Zoom. But that way you can be in front of your computers. We will be coding some of the things we're learning about today. That's what we're going to be up to. All right? So with that, let's talk a little bit today about dynamical systems. Here is a robot. This is a humanoid robot. This is the humanoid robot in our lab. It's called Digit, all right? And the way that Digit works, and you see it's walking and it's going to be stepping over this little tiny obstacle there. And it is controlling itself in the sense that we tell it to go in a certain direction and to avoid an obstacle, and it does it. And the way that it achieves this is that the robot has algorithms on board, okay, that have an understanding of their own dynamics, okay? Meaning it knows that its arms are a certain weight or a certain length. It knows its legs are a certain weight or a certain length. It knows it has motors at those joints. And it knows that if it applies a torque to the motor, this is the kind of accelerations that it's going to get. And with that, it's able to predict what's going to happen if it does one thing versus another thing. It makes decisions, optimal decisions, as to how to go about doing that thing, which is, in our case, make it walk. Okay? So, but a critical part of that is having a computer simulation, so that way we can, 1, test our robot out in simulation, but 2, that we know what dynamics to teach it. So here's a computer simulation of the robot. So somewhere deep in the robot, in its code, is a set of equations that tell it how it moves in response to stimuli. Okay? So, and here's some hardware results of us poking it with a stick. Okay? So poking with sticks is a long time-honored tradition in legged robotics. You poke it with a stick, see how it responds. So what we're going to cover today is our dynamical systems. Okay? So who here has taken any kind of physics before? Everyone, yes. Otherwise, I don't know how you got here. Okay? So you all know F equals ma, Newton's second law. Okay? I mean, force is equal to mass times acceleration. That's dynamics. Okay? That's specifically mechanics or rigid body mechanics. But dynamical systems is a much broader idea. Okay? In fact, it applies to almost everything. Okay? The heating of this room is a dynamical system. Okay? Sorry, get here. The heating of this room is a dynamical system. All right? Meaning that there are dynamics to it, meaning they change over time. And that's what the definition of a dynamical system is that it is a system for which key variables change over time in response to their current state or some input, okay? If there was no heating in this room, the room would eventually cool down and be the same temperature as it is outside, which is fairly cold, cold for Tallahassee. Have we lived here long enough to have a baseline for Tallahassee? This is cold for Tallahassee, right? Okay, right? Looking good, looking good over here on the technical? Great. Whew, glad. This was a lot of pain in the tush debugging here to get this all working. So even without any input, just the fact that the room cools down to the temperature of the outside world, okay? That's a dynamical system. Something is changing over time, okay? So it doesn't apply to just things like robots, right? So obviously I'm a dynamical system. I give myself a kick. I provide some kind of input or stimuli through my muscles, and I'm moving, right? Someone give me some other example of some kind of dynamical system. Anything. Ferris wheel. That's a great example. That was not on my radar. But yes, there's a motor on the Ferris wheel. You turn on the motor, causes things to swing around, right? And it's also things that are not mechanical or even thermal. We're all mechanical engineering, right? So you're typically doing things like dealing with thermal systems, dealing with mechanical systems, that kind of stuff. But biology, right? Chemistry, the rate at which a chemical reaction occurs, that's dynamics, right? So, but the thing that you've got to be able to do in order to be able to treat it as a dynamical system is define it as one mathematically, okay? So that's what we're going to talk about today, because all of these things and all of these different subjects, as long as there's a variable that changes over time, you could probably fit it in these equations that we'll talk about today. And if you can fit it in these equations that we talk about today, that's great news. You might be able to control it if you have that ability, okay? So, dynamical system. What is a dynamical system? Dynamical systems are systems which have variables, or called key variables, that change over time in response to stimuli or initial conditions. Okay? Very, very general. So initial conditions, we all know that from differential equations, but imagine a slinky. We all know, do children know what slinkies are these days? Is that a thing? Okay, they still exist. Okay. I never know what goes out of fashion these days. Take a slinky and you pull it. It's at a certain initial condition. And if you release it, wah, 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 right? Even though you've let go of the slinky, it's still moving, right? It was that initial condition that creates some kind of motion, right? And stimuli. Think of that as it can be a number of things, but we will think about that as a kind of control, right? I kick my leg. Whew. That's me applying a stimuli through my muscles, and it creates a motion, right? Key variables over time would be like the angles of my leg joints and things like that. So very super, super general, okay? So the key thing we want to highlight here is this change, okay? Now, there's an entire branch of mathematics that's about change. Anyone know what it's called? What's the math about? What math field has to deal with change specifically? Rhymes with schmalculus? Yes. Yes, that's right, calculus, right. It's calculus. Calculus is all mathematics about change. I don't know if they teach it that way, but I feel like that should be the first lecture. Calculus is about change, right? That's what the derivative is. The derivative says this variable changes at this rate as a result of this variable. That's the idea. So how we define a dynamical system, we define what we typically call an equation of motion, or dynamics. So we might have equations of motion where we will have some variable that changes over time, okay? Let's call it x of t, all right? This is some key variable, meaning it's a variable that actually matters to what I'm actually trying to study. You know, the color of a single particle on Jupiter does not change the state of this pen in any meaningful way. So that's what I mean by key variable, okay? All right, so what we'll define these equations of motion as equations about change or derivatives. And equations with derivatives we call differential equations, right? So you might have some dx derivative of x with respect to time. How much is that variable changing? Let's say this is the position of this pen vertically, okay? Well, it's a function of, could be a lot of things. It could be some function of the height of this pen or something. So this, and also it could be in response to stimuli, okay? This u of t, we'll call that a control input. Okay, and this x of t, we'll call it a state. Okay, think of the slinky. I should have brought one. It would have been much more visually compelling. Okay, you draw down the slinky, you release it. How much that slinky is accelerating depends upon the height of that slinky, right? If it's down here, it's going to accelerate up, right? Once it's released. Phew. If it's up here, it's going to accelerate down. Shoo, right? So how that slinky responds is the change in that slinky's state is going to be dependent upon the current state of the slinky. And also some control I might put on it. What if I push on the slinky? Let's say I pull it down again, right? Okay. So this equation here is so general, it can capture so many different kinds of dynamical systems, okay? Specifically, we're talking about ordinary dynamical systems. If you're doing things like heat transfer problems, you might have to model it with a partial differential equation. But for the purposes of this class, all the things that we're going to be wanting to model as differential equations, as dynamical systems, we're going to model in this way, okay? I'll give an example. Okay? Population modeling. Okay? One of the classic examples, right? So let's say you have some population P of t. And it's a population of rabbits. Okay? The more rabbits you have, the more rabbits they make, right? I believe that's science, okay? So the way we would write the equations of motion, the dynamics of this system, is we would say, oh, the population of rabbits changes with respect to time, and it's a function of the number of rabbits we already have, right? Okay? Let's assume no external controls here. Let's just assume that it's just the number of rabbits for the purposes of this example, right? Okay? The more rabbits you have, the more they're going to make more rabbits. So we could write this more specifically. If you were to talk to a population biologist and say, hey, a good equation to model it is that dp of t dt is equal to some proportional constant times p of t. Okay? where alpha is just some constant, and that's your rate of reproduction. Okay? Okay? Very simple population model. Okay? Now, you've all taken differential equations. You all know how to solve this differential equation by hand. Okay? Very simply, because you have a function that is equal to its own derivative multiplied by some constant, you could solve this by inspection, as we would say. And we would say, oh, that means if we were to solve this, p of t, that's going to be actually equal to some other constant c1 times e to the alpha pt. Because if you take the derivative, as we all know, of e to the something, it becomes e to the something. So it's basically equivalent to the derivative of itself. We pull out this constant, it actually all works, right? So if you were to take dp dt of that, it's going to become c times alpha e to the alpha p of t, p of t, and therefore because p of t is equal to c e to the alpha pt, that means that this and this become p of t, and therefore dp of t dt is equal to alpha p of t. Oh my goodness, this all checks out. Check. Great. Awesome, cool. Now I'm going to introduce some notation that's going to make your life a little easier. Notice that we write d something of t a lot, right? Does anyone know a shortcut? How to write this nicer? Yes. Yeah, a little dot. Yeah, a little dot. Well, so there's a couple of things. So specifically, you might be referring. There's a little dash, like the apostrophe, right, for derivative. That's a more general derivative. In engineering, it is so common to say a derivative of something with respect to time that we said that d of some variable, we'll call it p of t, dt. We write it as p dot. Oh, your carpal tunnel is going to be, thank you so much, right? Just a dot. What do you think p two dots, p double dot is? Second derivative with respect to time, exactly. Thank you. What's your name again? Christian. That'll be easy for me to remember. Okay. So that will be, that's the same as saying dp of t, their second derivative, right? Oh my goodness, saves me so much time, right? Okay. So get used to that dot. You'll be seeing it throughout the entire class. Okay? So you have this very simple equation that we can solve by hand. Now, what does that look like? Well, assuming that alpha is positive, and you have some initial condition, some p at time 0, and this is p of t, and this is t, it's going to be an exponential growth, breeding like rabbits, right? Exponential growth, the exponential curve. Okay, dynamical system. Now, any questions about that? Very simple. How could this all be hard, right? This is not too bad, right? So this is stuff we learn in calculus. Now, question is, so this equation, though, is a very special kind of equation, a special kind of differential equation in a couple of different ways. Anyone know what the order of a differential equation means? Anybody? The order. Yes? The highest derivative. Highest order derivative. Correct, Marco. So what order differential equation is this? First, because there's a first derivative, p dot, a single derivative. Okay? So also, this is what we call a linear differential equation. Okay? You'll notice that that all the terms, they are all just added to other terms multiplied by constants. We'll talk more about linearity in a bit. But if this was P dot is equal to sine of P of t, nonlinear. Okay? That can make it a little trickier to solve by hand. Okay? I'll give you an example. This is an example that you will see a lot in any controls course that's based out of mechanical engineering, even electrical engineering. Okay? And it is our dear friend, the pendulum. We will be coding the pendulum on Thursday. We'll be coding it in MATLAB. All right? Okay? We have a pendulum under gravity. All right? Now, we could use physics. We can use physics 1 to solve this differential, to come up with the dynamics of this system. In fact, we can kind of do that. Let's define our angle of this pendulum, theta of t, relative to the vertical. All right? Let's sum all of the torques about this point O. Sum all the torques about O. Okay? We're going to have a length of this pendulum, L. And some of the torques is going to be equal to your moment of inertia times your acceleration. So you can have some moment of inertia, I, and the acceleration of that angle. Sometimes you'll call that alpha. But using our fancy new notation, what's the second derivative? How would you write the second derivative of theta with respect to time? Theta double dot for the acceleration. Theta is the position. Theta dot is the velocity. Theta double dot is the acceleration. Theta triple dot. Jerk, jounce. I've heard jolt before. That's new. Yeah. We won't be doing much in these. These are just fun. Okay. A fourth derivative. Snap. Fifth derivative. Crackle. Sixth derivative. Pop. That's right. That's right. I tried to find the first people to actually invent this. It is literally a Rice Krispies reference. Okay. That is not a joke, and that is actually true. I only heard anecdotally from someone who had access to some of the code for the 1960s moon landing, for the moon lander. And they said there were references to snap, crackle, and pop in that code. And I said, can I have it? He's like, I don't have it. And I was like, dang it, because I was trying to find the earliest reference to snap, crackle, pop in the engineering literature. Anyway, couldn't find it. But anyway, this is I, some moment of inertia I. Who learned that today? Some of you. Good. All right. Here you have your moment of inertia. It's like your mass, but for rotations, times your acceleration, which we know is theta double dot. My little double dots, right? Okay. Those are your equations of motion for this rotating object. Okay. So if you look up in your engineering textbook, when you have a mass that is rotating at some distance L, the moment of inertia is going to be mL squared. So point mass, so that's fine. And the sum of our torques, what are our torques? Our torques are actually just due to gravity. mg pulling down over this lever arm right here, okay? And using the power of trigonometry, we do know that it's this trigonometric right angle right here, where we have the hypotenuse L, and we want to know what that is. So it's going to be L sine of theta, that's our lever arm, times the force mg. That's going to be the torque on that pendulum. And technically, the way that it's defined, if you use the right-hand rule, I've defined my theta t. You curl your right hand into the direction of where theta t is pointing. You can see this pointing like right there. Like that. So out of the board, that's positive. Okay? But when you have a positive angle, this torque is going to be pulling us backwards, right? So that torque is going to be negative. when you have a positive theta of t. So negative. Okay? So if that's the only torque on our system, we have not applied any external motor or anything. So therefore, this term here is going to be minus mgl sine of theta. I trust that you all trust my algebra with that. Going from there to there equals to the right-hand side ml squared theta double dot of t. And I forgot my of t here for sine of theta. I'm just going to rearrange this. I'm going to sillily move this to the other side because it makes it look familiar to me. And then I'm going to move, so it's going to be m L squared theta double dot of t is equal to minus mgl sine of theta of t. I'm going to divide both sides by L squared. There's a single L on the right side, so when I divide it under, it's going to be minus mg over L sine theta. Also, I see an m there. I see an m there. Gone. This all turns into theta double dot of t is equal to minus g over L sine of theta of t. Not bad, right? Okay. Voila. These are our equations of motion for that pendulum. Okay? Now, what order differential equation is this?
Second.
Second. Why is it second? Because you have two derivatives here. Okay? This is a second order differential equation. Diff EQ. Okay? And because it's an ordinary differential equation, and when I say ordinary, meaning there's a derivative to only one type of variable, and that's time, and that's what we will be mostly dealing with when it comes to our dynamical systems. It'll be a little different when we get to the optimization side, just to be clear. We will deal with partial derivatives then. But it's an ordinary differential equation, or ODE. So second order ODE, okay, is what we would call it, right? So is it a, for those who are inclined to guess, is it a linear ODE? It is not. You're shaking your head so emphatically. Why is it not a linear ODE? Because that's sine, right? That makes it a little bit trickier to solve. Does anyone know how to solve this differential equation by hand? The answer is no, because it's impossible. Proven impossible to solve this, to write out an equation that is the solution to this differential equation using anything that we recognize as elementary mathematical functions. You can't do it with exponentials. You can't do it with sines and cosines. There is no solution. Okay? What? How could that be? We simulate pendulums all the time. I mean, who here has ever played like a video game with like physics in it? Yeah, exactly. When everyone, like a character's like ragdolling or things like that. Those are pendulums attached to other pendulums. It's even more complicated, and yet we simulate them. What the heck? Well, there is no exact solution for the pendulum under gravity. Specifically using what we call elementary functions, to be technical. Okay? No exact solution. That, in contrast with that population model, we could absolutely solve that. Solve it by hand. That is the exact solution. C, e to the alpha t, exactly correct. No exact solution here. So the key here is the exact. So what we do instead is come up with an inexact solution, an approximate solution. Okay, that's how we simulate these differential equations. So just to add a little bit of extra here, let me just a little extra context here. So since we have this differential equation, right, we can now simulate how the population would evolve over time, how those key variables will change, in this case the population. But there it was easy. because we have the answer. It's this. At any time t, it could be 1 billion years into the future. All you got to do is pop in 1 billion, you can pop in 1 billion years into the t. Sorry, you pop 1 billion years into the t here. Okay. Did I screw up? Did I accidentally write p of t up here instead of t? Okay, I really apologize. I got feeling my oats here. Just cross out here alpha t. This is just t. P to the t. There you go. That's it. I'm sorry. No one called me on that. You were testing me, right? Okay. You just plug in t right here. You have your answer, right? Okay. However, that's not the case for the pendulum. You have to use methods to approximate the solution, and they become a little bit more computationally intensive. We have to do a little bit more calculating. Okay? So for instance, here's one way that we could approximate. So we want to approximate the solution to a ordinary differential equation, to an ODE. Okay? Let's go back to the population example. Let's say we didn't have all of our differential equations knowledge. We wanted to solve it approximately instead. Let's do the example of the population. Population growth. Okay? So we have dp dt, or otherwise known as p dot, is equal to alpha p of t. Okay. Gesundheit. That was the softest sneeze I've heard in a while. All the ones are so soft I didn't hear them. So, p of t. So what's a way that we could try to come up with this plot to know what the population is over time? And there was a yeah, there we go. This population over time, if we don't have the exact answer. Well, first off, we need to know our initial population, some p0, an initial population. Okay, let's say it's right there. Population p of 0. P at time 0 is there, okay? Now, we don't know offhand what, in the future, what the population is going to be, okay? We're going to try to approximate that. But what we do know is how much the population is changing over time, okay? So the change of this vertical variable with respect to some horizontal variable on the plot, rise over run, what's that? Slope, right? The slope. We commonly think of the derivative as the slope, okay? So let's say we calculate, hey, we're currently at time 0. Let's take our current population at time 0, multiply it by alpha. That's the slope. So let's actually draw whatever that slope is. Let's pretend it's like this, okay? Whoop, slope. And we just go for a little bit of time for that slope, just a little bit. And we say, okay, where do we end up? We end up right there. And now we're at some new time that's not 0. Well, let's take that new population, which is a little bigger, put it in here, multiply by alpha. And that gives us our new slope, right? Which is going to be bigger. Okay? Move ahead a little bit in time. Now we have a bigger population. Now we're going to have a new slope by multiplying by alpha. And continue, right? Now, is this an exact answer? No. This is an approximate answer. And that's just based upon the intuition of what a derivative is, okay? But this is also mathematically, of course, what a derivative is. Keeping in mind that a derivative, okay, jumping ahead a little bit, This is what we would call an iterative approximation, okay? We are basically taking our first time point, marching forward a little bit in time, checking again, marching forward a little bit in time, checking again. This is a time marching iterative approximation. Okay? All right? So you get the idea, it's sort of marching forward in time? You get that? Do I have to march across the room to get it? Yes, question?
Is it discrete or continuous?
They have to be discrete as opposed to continuous. Otherwise, how far will you step? Like infinitesimally small. But you're coming up, I'm going to put words in your mouth and say, yes, these steps, you can make them super, super, super tiny, right? Why would you want to make them super tiny? Why do you think?
I mean, same thing for calculus, like you approximate the interval.
Yes, yes. And it would make this approximation more accurate, right? Why wouldn't you want it to be infinitesimally small? Practically. Yes, question. Yeah, answer.
Resolution, like the more you increase it, the more time such that it will
Yeah.
spend.
The more time, more computational time it would take. I mean, exactly. So, if you're monitoring rabbit populations over the course of years, do you have to take picosecond, little steps? No, because it's a waste of time. And what are you going to get out of it, right? So there's a trade-off, right? So yes, these are discrete steps forward, okay? And let's unpack that a little bit, okay? But what I want to point out, and I want to hammer this home, is that whenever you see anything involving computer simulation, whether it's in a video game or in a laboratory or some kind of research outcome, okay, simulation is just solving differential equations, okay? So, and some equations, as we found, you cannot solve exactly, so we solve them approximately. There are many ways to solve them approximately. There are different levels of sophisticated. We'll cover a few of them in this class, okay? But just want to get that in your head, that simulation is just solving differential equations. Boom. Okay? So, back to, so how does this work? Well, the answer goes back to what a derivative even is in calculus. Okay? So what is a derivative? So let's say you have some derivative of some function x with respect to time is equal to the limit as some change in time goes to 0 of some x of t plus delta t minus x of t over delta t. That's basically how far does your vertical variable change or when your horizontal variable changes as that limit goes to 0, right? Now, practically computationally, you can't make it arbitrarily close to 0. But what if instead delta t is small, but not approaching 0, okay? That would mean that the derivative of x with respect to t is approximately equal to x of t plus delta t minus x of t over delta t, where delta t is small. Small steps, little tiny steps that march forward in time. Now, of course, in calculus, time is not the only thing you can take a derivative with respect to. We certainly will be at other points in this class, but we're just keeping the notation the same here, okay? So, we have this approximate formula, right? And what the thing we want to find when we are solving a differential equation, we want to know what our variables are like in the future, the population in the future, the angle of this pendulum into the future, the position of this robot, the state of this chemical plant, etc. We want to know what it is in the future. What's happening in the future, friends? So let's solve for the future. Let's solve for this term. So multiply on here, we got dx dt, which I will now call x dot of t times delta t. So approximately equal to x of t plus delta t minus x of t. Now I'm going to put this on the other side and then just switch the equations around so that's on the left. So it's just going to be x of t plus delta t is approximately is equal to x of t plus x dot of t delta t. Boom. Okay? And this is called Euler's method. Okay? Some people call it forward Euler. There are a few names for it. Okay? It's spelled Euler, but cool people call it Euler. I could say this with authority because my postdocs advisors was Leonard Euler. So I'm an authority. Okay? So, and this equation encodes exactly what we did with that example up above, with the population model, with that iterative time marching step, right? It said that, hey, where you are next in time, okay, boom, is equal to where you were in time, boom, plus x dot of t, which is your slope, times the time step. That's all it is, okay, right? That is the speed run way to solve differential equations that you otherwise can't solve by hand, of which there are many, 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 okay? Some of those robots that I was showing at the beginning of lecture, okay, I mean, their equations of motion were much more complicated than this, okay? In fact, frequently we will no longer solve those, we will no longer do the equations of motion by hand. We will no longer like do free body diagrams. We will use what's called Lagrangian mechanics, which we will learn. And it's quite fun, okay? And you'll have a to set up the equations, then you'll have a computer algebra system, such as Mathematica, or in our case, MATLAB, to generate those equations for you, okay? And the equations of motion, if you had printed them out for one of those walk-in robots on paper, people used to do this. They used to print things on paper. It would cover 2 football fields, okay? So you're not solving that differential equation. You're doing it numerically. So we're doing it approximately, okay? So Euler's method is an approach for approximately how are we doing here, Nick? Some drop, okay. Or what we'll sometimes call numerically solving ODEs, okay? It's the simplest one. Back when I learned differential equations, we taught a method called Runge-Kutta methods. There are packages in all kinds of programming languages, including MATLAB, which will automatically do that for you. And we'll cover them on Thursday, okay? We'll code them up. Basically, you can use more information about the derivatives in order to make it more and more accurate. So you don't have to have tiny, tiny time steps. Or, frankly, things like Euler's method, they can sometimes be unstable approximations. But the point I want to make is that we do a lot of approximate solving, or sometimes we call it numerical solving. Okay? All right. Now, you'll notice, if I look at that equation, this looks like this looks like a method of solving only first-order differential equations, right? I'm looking at that equation right there on the board. I see a single dot. If I had 2 dots, okay, that's not covered by that directly, right? Gesundheit. And we will definitely want to do second-order differential equations. In fact, we will have many higher-order differential equations, not because we're caring about jerk, snack, crackle, pop, okay, but because we'll have multiple variables. Instead of x, it'll also be y and z. I mean, think about it this way. Okay? I had this marker here. Okay? All right? If it only moved in one dimension, I could describe its motion using F equals ma. You know, its position governed by its acceleration. So that's a second-order differential equation. I have to care about the position, the velocity, and this acceleration will dictate it, so it's going to be a second-order differential equation, up and down. Now what if I want to also move left to right? I got to add 2 more orders. Now what about forward, backward? 2 more orders. What about rotation? That's another. But there are 2 other axes of rotation. There's yaw and roll. I think I gave you pitch. I'm not sure which one I gave you, but I gave you, that's 12 orders of differential equation to do that. And even more if you want to catch it. Okay? So we need a way of approximating the solution to differential equations of higher orders. Otherwise, you can't do that. Pretend I did it. Right? So the good news is that there is always a way to take a higher order differential equation and turn it into a bunch of different first order differential equations. There's always a way to do it. Okay? All right? And that's what we'll show you today, because we'll need to do it for our coding lecture on Thursday. So we need to turn higher order ODEs into multiple first order ODEs, what we sometimes call a system of ODEs. Okay? And the way that we achieve this is by adding more variables. Okay? Let me give you an example. Let's just say we had some differential equation, s double dot of t is equal to minus s of t. Okay. This is actually the differential equation describing a spring mass system, a slinky, more or less. Okay? Okay. Second order differential equation, right? However, what if I added another variable? Okay? We have s of t, let's just say that that is the s of t is some position. Okay? Obviously, s double dot of t would then be what, friends? Acceleration, right? What if we added another variable? We'll call it v of t, which is the velocity, or s dot of t. Let's just say we did that. We had the foresight to know that that was a good idea. Okay? I've defined f of v of t as being the derivative of s of t with respect to time. Now I'm going to go back to this equation. S double dot of t, that's the same as v single dot of t, right? S double dot of t is equal to v dot of t. We're all cool with that, right? And on the other side, minus s of t, so it's equal to minus s of t. So if I look at these two equations, v dot of t is equal to s dot of t. Sorry, v of t is equal to s dot of t. And v dot of t is equal to minus s dot of t. What's the order of one of those differential equations? 1. What about the other one? Oh, sorry. I only see a 1 dot here in that equation, and 1 dot here in this equation. Two first-order differential equations. And I can use Euler's method on each one. Voila. By adding a variable, they're now first-order differential equations. I can now use Euler's method. I can use these methods. Okay? That's the technique we're going to use. And coincidentally, it actually unlocks an entire set of techniques that's super important for controls. You'll see that there are now 2 key variables, s of t and v of t. So we'll put them in a little list or a vector. S of t and v of t. These are our key variables. They're in a vector. Did I hear someone say state vector? Did someone say state vector? Who said state vector? Point them out. Yes. Good job. Yeah, they're embarrassed, but yes, it's a state vector. Okay? I have walked you backwards into this concept that's super important in controls called a state vector or state space. This is called a state vector. Okay? In essence, we have just created a vector that contains every important variable that we need to solve the differential equations using first-order techniques. Okay? We can use it to do Euler's method and other time-marching integration methods. Absolutely we can. We can also use it to write some really simple equations to describe some of our systems. And we can use it to control systems really easily, like really easily in the scheme of things. Okay? So it's called a state vector. So basically, each of these variables, these key variables, they're called state variables. So these are state variables. Okay? So state variables are the key variables sorry, I wrote this wrong, are the minimum key variables necessary to predict the future evolution of these variables if all initial conditions and control inputs are known. Okay? The fewest. So to know the future trajectory of this slinky, I do not need to know the position of Jupiter. Okay? Unless you're really into gravitational effects or something, you know. So the position of Jupiter would not be a state variable, okay, for that slinky, right? So it's the fewest number, okay? That's an extreme example, but it also counterintuitively means acceleration is not a key variable, okay? Because we compute the acceleration of the slinky using the position. It's stretched or not stretched. There's not some separate variable you need called acceleration. All right? So a state vector is a vector containing all state variables. Gesundheit. All state variables. Okay, I'm going to do something here. I'm going to go scroll back up. I'm going to put a little bar over x to indicate that it is a vector. Okay, I may or may not do that into the future, but I just want to make it clear that because it's a vector, it contains multiple variables in a vector. Okay, and as a rule of thumb, we will be using x as our state variable, as our state vector. Okay. We are in an interesting position as we are in an optimal controls class. A lot of times in optimization, x will be the decision vector. Remember that from last lecture, right? Okay, that's why I called it w for the decision vector. But so fair warning, when I'm talking through optimization stuff, I am doing my dangdest to go all through all this stuff, but I might accidentally write the decision vector as x. That's just force of habit, but I will always try to write it as w here. So that's a state vector, okay? Now, when you're learning about vectors, you might have had them described as being something like this, something with a tip and a tail, right? A vector. Right? And so that vector is on a space. Okay? So this is a really simple way of saying this is why we call it state space methods. Okay? So if you say, here's someone calls something state space, it means that there are state vectors involved. And yes, you can draw vectors on a state space. Okay? Sometimes you'll hear something called state space controls, which we will be covering in this class. State space is a vector space of state variables. That might sound fancy to some of you. Don't be alarmed. But think about it this way. If I have this slinky, you don't have a slinky on you, do you? Okay, all right. Just checking. If I have a slinky, you pull it, it slinks, it slowly decays, right? Okay. This slinky has two state variables, position and velocity. Okay? So let's say you have a position here, s, and a velocity, v. If you were to plot what that slinky's motion is on state space, it might look something like this. You might have heard something called a phase plot in differential equations. It's the same thing, but state space could be higher dimensional. Let's go back to my example of this marker. We're talking a 12th order differential equation. It's going to have 12 state variables to do that. Okay? I'm not plotting a 12-dimensional plot. Don't even ask. Okay? But it's a conceptual space, right? Right? So that's great. That's nice. I'm glad you think so. And the question is, is there a way to take any ordinary differential equation of any number of variables, any number of equations, and just have a very simple way of turning it into state space, having a state vector? Because if you can write your equations in what we call state space form. Okay? And for any ODE, it could be written as x bar dot of t, because the states are dependent upon time, is equal to some function. I'm going to call it h, but you can imagine it as f. It's only because we use f as a cost function in optimization that it's already taken. Is dependent on the state and any control inputs. I'll define these here in a second. So this is our state vector. This is our control input vector. Okay? If you can put it in that form, you're golden. Means that you can put it into MATLAB and simulate it. Okay? Right? And we did this for the pendulum. Okay? Our pendulum, x bar of t, this is the state vector. It had, we didn't do it with the pendulum. We did it for the slinky. Yes. X bar of t is equal to s of t and v of t. Therefore, x bar dot of t, that dot is the time derivative of x. If you want to take the time derivative of a vector, it's actually really easy. Just take the time derivative of everything inside. That easy. S dot of t, v dot of t. That's great. Now, on this side over here, we can write all of these values here in terms of states. Yes?
So how come acceleration is not a key variable while velocity is, and it's also a derivative of position?
Great question. Can we hold that for like 30 seconds, and maybe it'll become more clear? Okay? I'll show you don't need it, is what I'm going to show. What's your name again?
Riley.
Riley? Thanks, Riley. I'll show that, so the question was, why isn't acceleration a state variable? And I'm going to show that you don't need acceleration as a state variable to represent the equations. Okay? And if you don't need it, it's not a state variable by definition. It's not minimal. Okay? So s dot of t, can we write that in terms of any other state variables? And you have to go scroll up in your notes, and you will see, wait, where did I do it? Let's scroll back past it. There. S dot of t is equal to v of t. Is v of t a state variable? Yes. Yes, it is. Okay. So that's equal to v of t. Right? They're the same. And v dot of t, that is your acceleration, Riley, right? But we have an equation for acceleration from our slinky. It was this minus s of t. Okay? So, minus s of t. Okay? So, you could say that, hey, friends, x dot of t is equal to v of t and minus s of t. And this is a function of only state variables, none of which are acceleration. And it is a common and understandable trap to want to throw in acceleration as a state variable. Okay. So you don't get in your own head. I want to give you a procedure for knowing exactly what is a what state variables you need and don't need. Just looking at the equations that you're starting with. Is this going in the right direction for you, Riley? Thank you. Thank you. All right. Doing okay? Great. I'm excited. All right. Recording there. Okay, so here's a procedure for putting any ODEs into state space form. Okay, and it even handles really tricky cases. Okay. Who here took controls 1? Okay. Anyone here heard of, or anyone heard of a PID controller? Yes, okay. Anyone to tell me just roughly what a PID controller is or what the PI and D stand for? Anyone? Yes, in the back. Proportional, integral, and derivative control. Correct, okay? Which means that these control inputs here, and I should say control inputs are things that you decide, okay? Right? I can't arbitrarily decide that my pen is now on the moon. I can't do that. it has to get to the moon via its own dynamics first. Some rocket has to launch it there. If I want to get my pen over there, this is expensive. I'll use the other one. Get it over there. I had to throw it in a certain way to get it over there. I can't arbitrarily put it where I want it to go, right? But a control input, I could say, you know what? Right now I'm going to apply 10 newton meters of torque within the limits of what I can do, which I have limitless muscles, as you can no doubt see, okay, right? So I can arbitrarily decide which way I want to try to move, which way, how much force I want to put in my muscles. Like I say, I want it to go this way, this way, this way, this way. I get to choose it. Therefore, if I get to choose it, it's a control input, and that's u of t. And because it's a vector, you could have many of them in a list, right? So, okay, procedure for putting any ODEs into state space form, okay? So, step 1. Find the highest and lowest order derivatives for each independent variable. Okay? And we'll go through with an example from top to bottom, so we're following it along, okay? So let's just have an example, and it'll be a system of differential equations. They do not need to be linear. It works for nonlinear too. We haven't talked much about linearity yet, limits for one lecture, okay? But let's write, so we've got, someone pick a letter. Pick any letter. C, good choice. Okay. Let's say C dot of t. Someone pick another letter. D is equal to D of t. Pick another letter, please. J. Good choice. Plus J double dot of t. Okay. All right. I'm going to write another equation. I'm going to say D dot of t is equal to C of t, and J triple dot of t is equal to J dot of t. Sorry, that's a dot. I shouldn't have done a J because it has a dot, but that's okay. I blame myself. I blame myself, but it's pretty clear that's a dot, not a J, right? I'm glad you all agree. Okay. All right. That's our differential equations. Those are our equations of motion. What that's for, heck knows. I don't know. I just made it up. It's arbitrary. It's crazy. I'm going to put it in state space form. Okay? So find the highest order derivatives for each independent variable. I count 3 independent variables, C, D, and J. Okay? Different letters. Okay? So for C, the lowest order derivative, so we're going to lowest is, I see C of t. That's a 0th order derivative. It's not a derivative, right? So it's 0. Sorry, we'll do, I apologize. Let's do highest first. I'm sorry. I hate to make you erase. Highest. Let's do the highest order derivative. The highest I see is C dot, right? C dot. And the lowest is C. So that's the highest order is 1, single derivative. And the lowest is 0. What about for D? For D, I see the highest is 1, lowest is 0. Okay. Now for J, the bane of my existence, J. What's the highest order derivative you see? 3. Doing some kind of jolt thing here. What's going on? 3. And the lowest is what? 1. Okay. All right. Okay. Now I want to subtract the lowest from highest. and add the results. So 1 minus 0, mathematicians will tell you, is 1. 1 minus 0 is also 1. 3 minus 1 is 2. Add them together, 4. There are 4 state variables that you need to represent this. That's the number of state variables. The result is the number of state variables. Okay? Number of state variables. Okay? Pretty easy so far, right? We're counting and subtracting. I put a lot of thought into this procedure to make it as simple as possible because, Riley, you're like the 30,000th person to ask me, why not acceleration? Well, let's go back just a little aside here. Do our equation, right? S double dot of t is equal to minus s of t, is equal to minus s of t. What's the highest? It's 2, right? Lowest is 0. It's 2 state variables, position and velocity. Well, let's get into why it's position and velocity, not velocity acceleration, or at least the procedure that'll give it to you, okay? And because this can trip people up, and especially when you have things like PID controllers involved. The I stands for integral, right? That's like the opposite of derivative. So if I had an integral of something with respect to time in this equation, you know what order it is in terms of my little system here? -1. And my system still works. It's that cool. Okay? So what that means is, for those who have experienced this before, if you have an integral in your differential equation, you're going to have to add another state. Okay? All right. That's the number of state variables is, in this case, 4, using that procedure. That's step 2 was subtract. Okay. All right. Now number 3. This is a big one. Write the state vector and then its derivative. Okay, so let's write the state vector. We'll call it x of t as the state vector. In this case, okay, I guess I got to tell you what the state vector is. I'm so sorry. Write the state vector and its derivative. So for each variable, I'm going to make a little space here. I apologize. For each variable, list the lowest order derivative and every higher order derivative until the highest. So you want to exclude the highest. Okay. So you want to count up all the higher derivatives, but you want to leave out the highest one. So we had c of t. That's the lowest order derivative of the c's. Let's count up to the next derivative, c dot. Oops, c dot is the highest order derivative. Do we use it? No. No, we don't. D is the lowest order derivative of d, right? Now we count up d dot. D dot is the highest. Do we use it? No. Okay. Now what's the lowest order derivative of j? J dot. Okay. What's the next higher order derivative of j? J double dot. What's the next higher order? J triple dot. Do we use it? No, because it's the highest. That's our state vector. Okay? Now let's write its derivative. So this is the trick of the state space form, that because the state space form takes a derivative of the state vector, you end up having the highest order derivative in your equation, right? That's why you don't include the highest order derivative as a state, because it shows up here anyway. So x dot d dot of t, j double dot of t, and j triple dot of t. Boom, boom, boom. How are we doing, Nick? Great. All right. Finally, step 4. Write in state space form. Okay. What this means is that you have to write the derivative. Specifically, you need to write the state derivatives in terms of states x of t and inputs u of t. Okay. Because this is the state space form that you want. X dot is equal to f of x of t u of t. I have this on a mug. I love it so much. If I got a tattoo, it would be of that, with slightly better handwriting. Yes?
It is 10:44, just so you know.
Thank you. We're almost done. You're on the ball. Cool. All right. So just to finish this off, that means that we have our state derivative. We wrote it in terms of this. Now I have to write it in terms of state variables on the right. So c dot of t, d dot of t, j double dot of t, j triple dot of t. Then on the right, we've got to write this all in terms of states, because again, as we know, j triple dot of t is not a state. However, if we go up to our original equations, j triple dot is equal to j dot, which is a state. Because we're so smart, we set this up perfectly. There's always a way to do it. J dot of t. C dot of t, oh, there's an equation right here. D is a state. J double dot is a state, right? C, D, and J. J double dot. D dot is not a state. However, it's equal to C of t, which is a state. Okay. Guess what? J double dot is a state. Done. Okay, it's in state space form. We're at the end of the lecture. So I just wanted to, parting words here. Coding lecture on Thursday. I will send out a Zoom link to everyone to join. Okay, you could always join via the stream, assuming that all works as well. But you can talk to me over Zoom. I can take questions. I got headphones in and everything. I showed you this as an example. It's got lots of weird equations in this example. There's always a way to do this, but you might have to manipulate the equation first. Maybe the j double dot's on another side, or maybe you have to solve a system of linear equations, but there's always a way to put it in this form using this procedure. So with that, thank you all so much. Talk soon.